Welcome to the April meeting of Columbus Astronomical Society. Yeah. So. I'm glad you all found the location after a little couple misstarts we had there. But it looks like most of you found it okay. So welcome, and we're going to lead right into it. I guess we'll have Don say something first about his trials and tribulations.
All right, good evening, folks. Yeah, sorry had to put you through all this, all scrambled at the last minute and stuff like that. Essentially what happened was one of the sewer pipes for the observatory collapsed and clogged and backed up in the building, and so it made a humongous mess, as you can well imagine. I came in one day and discovered 6 inches of water standing in the basement. It's unfortunately taking a lot of time to get things cleaned up and figure out what we're going to do going forward with this. So I appreciate your patience. I'll keep the officers in the loop, and in turn, I'm sure they'll pass the word to the membership as far as what we're going to be doing in the future. I'm hoping to get things back up and running by May, fingers crossed, so we'll see. I've also reached out to some folks at the university, and going forward, I'll have the ability to arrange for space up on the main campus of the university to host meetings for the club if you guys so desire. They'll be at the Science Center on the main campus of Ohio Wesleyan University, and there's plenty of parking, restrooms, all that kind of stuff there. I'm also going to have a big ask for you guys. One of the things I'm trying to do to kind of encourage university to take care of the place and show its value, I decided to schedule a kind of a special stargazing program on the main campus of Wesleyan at Selby Stadium. That's kind of the big football stadium up there on campus. And agreed they're going to turn off the lights of the stadium. We're going to set up in the field out there and do a little stargazing night on May 9th from 9 to 11 p.m. And so I'm asking folks to bring up their telescopes, set it up. And for the folks at Wesleyan, there'll be a lot of Ohio Wesleyan parents there and students. That's the night before commencement for Ohio Wesleyan, and so I'm hoping to kind of garner that kind of support on campus, and it'd be an opportunity for the club to make a good impression on the administration of Ohio Wesleyan as well. And you can add your voice to mine as far as, trying to preserve Perkins and keep it going. So I'd appreciate all the support you guys have shown so far. And again, if you can come help with that program, the only contingency is it's got to be clear, unlike Perkins, where I can do other things. For this, it has to be a clear night. Even if it's partly cloudy, I've scheduled it where on that night there's a moon at least and some planets to see. So even though it's in the middle of Delaware, we'll be able to do some observing there in the field if it's clear enough. So do come help with that if you can. So, thank you. 9 to 11 p.m. May 9th. That's Friday night.
Good. Only the break.
Okay.
So you're doing CAS next.
Thanks.
It's cool.
I've been wondering what that beeping thing is. It's kind of interesting. Anyways, hi everyone. I'm Jason Hissong. I'm one of the members of the CAS group. It's the imaging special interest group. So anyways, Isaac is out of town, so he asked me to run the meeting next week. for those of you who are interested and are on the email list, I'll be announcing where it's going to be. It's probably going to be at the Hilliard Public Library. I just got to make sure that we have a place to get together. I'm going to be doing a tutorial session on how to process C-star images with Pixel Insight. So watch for the email to come out on the CAS's email list, and hopefully we'll see you then. And it will be, we usually get together at noon. Is that right? I think we get together at noon for lunch, and then afterwards we go and do the meeting. But just keep it up. Yeah.
No, the meeting is usually at 1.
1 p.m., right. So we get together at noon for lunch, 1 p.m. for the meeting. So anyways, watch your email if you're on the CASIS list for an announcement. That's it. Thank you.
Okay, so, let's see, our outreach coordinator isn't here today, but we've got a couple of events coming up. I think they're mentioned in the email or the newsletter. We'll double check.
Bexley is on May 8th.
May 8th, yeah.
And there's one in Ron. Yes.
Yeah, July, I'd have to get the date. Okay, you got anything, Brad?
I'll say a few things.
Okay.
Yeah. Speak.
John Glenn Astronomy Park is currently doing programs on Clear Friday and Saturday nights, as you guys know. I see a number of the volunteers that show up time after time, and I really appreciate it. If you guys would like to come down and help out, we do have a truly dark sky, and it's actually very nice to observe afterward. A lot of people, bring their imaging scopes and take pictures and that sort of thing. But you're welcome to use it, not during the program as well. I just wanted to make an announcement. This is a tentative announcement. We're looking into doing a fundraising concert at the astronomy park, and we're going to sit everybody in the field, and then we'll put some. It's going to be an orchestral concert. We're getting an orchestra to play. We want them to play like Holst or something like that. Everything hasn't been nailed down at this point, but we're hoping to get as many people as possible. This is something I'll let everybody know, what's going on when it finally gets settled, if it gets settled. I really wanted Eric, who is the other guy that I work with at JGAP. He was planning this whole thing. He wanted to get a Pink Floyd cover band that was going to play, that specialized in playing the entire Dark Side of the Moon album from beginning to end. Somehow the board of the Friends of the Hocking Hills didn't find that to be in their wheelhouse, and I'm thinking, why? I mean, that's very stuffy. So we're going to try to they want to class it up a little bit. Our current president is very much in the white tablecloths, high heels kind of camp, and we want more the sweatshirts and the branded T-shirts, kind of camp. So it may actually turn out that we get a Pink Floyd concert if we can convince them that this is something cool to do. So, but this is going to take place. They were asking me, what's a good day for it, and I was thinking we were going to do it sometime around the Perseid meteor shower, so that then people would have something to do after the meteor shower and that kind of thing. But so stay tuned for that. That's pretty much it. If you guys want to come down and volunteer, thank you. Appreciate it. So, yeah.
Okay.
Yeah.
So, we're going to try to work on getting some more viewing opportunities together, some evenings where club members can get together and have a mini star party, if nothing else. So we'll be announcing, what we come up with. It's weather dependent. Last spring we tried to do that, and it seemed like every time we got rained out. So we'll keep working at it. But we've got a guest speaker tonight, so you want to introduce our speaker? And we'll continue on.
a lot of you guys have probably already seen him because I've seen you do the new Vistas a few years back, and so you guys are probably familiar with him. I just want to say thank you for being incredibly willing to change plans 2 times and being completely mellow about it. You didn't seem like it bugged you in the least. So I really appreciate your chill attitude about the whole thing. And for you guys, this is Professor Mark, and I'm going to say your name, Pinsonneault? Pinsonneault? Okay, from Ohio State University. And he's going to be talking about astroseismology and the Roman Space Telescope, which, as you guys don't know, is a new space telescope that's slated to go up, which I have been describing to people as the Hubble on steroids. Basically, it's the Hubble with a really, really wide field of view. So, I mean, if you could imagine, like, taking, instead of 200 pictures to get the Andromeda Galaxy, maybe what, 2 or 3 to get the Andromeda, 1 to get the Andromeda Galaxy, yes. So you can get the entire Andromeda Galaxy at Hubble resolution in 1 picture. So this would be an amazing way of doing like really cool wide field surveys and that kind of thing. So we will get you set up with the sound, and we will let you get started. You can put that in your pocket. And if you put that on your held here.
All right, we'll see if we can make this work. Testing, testing, testing. Sounds good.
Yes, it does.
All right. And thanks very much for the opportunity to come here and give a talk. There's some really exciting work we're doing. Ohio State is actually very heavily involved in the Roman telescope mission with a number of different teams that are invested in different things. Some people, like Dave Weinberg and Chris Harada, are interested in using it for cosmology to study the long history of the universe, the origin and nature of dark energy. Other people, like Scott Gowdy, are interested in using it to search for planets. And I am very interested in using it to look at stars in the galaxy. And I listed the team here because one of the things I thought might be interesting for people to know is this kind of structure is how a lot of science is done. And so this is the group of scientists that I have listed on here who are the people involved in trying to study whether we can use the Roman telescope to figure out the ages and properties of stars in the center of the galaxy. Some of these people are international. Tim Bedding and Dennis Stello are from Australia. Dan Huber is from Hawaii, lucky guy. Joel Zinn is from California. Mark Hahn is at MIT. Then we have several undergraduates and graduate students, Kylie Cow, Noah Downing, Trevor Weiss. We have Jennifer Johnson here, who is a liaison to One Survey. Sanjeev Sharma, who's at Space Telescope, who's with another. And we also have Matt Penny at Louisiana State and Scott Gowdy at Ohio State to help us. So this is the kind of effort you have to put together to kind of try and make this thing work. Everybody has a task. There's a bunch of different jobs that are involved. I'm project lead on this particular thing, and I do a lot of work on understanding the properties of stars. Now, I always like to start with a motivation image, and in this particular case, there are 2 big reasons why you might want to really study the properties of stars in detail. You might really want to be able to understand interesting things about the galaxy. One of these is to understand the origin of the elements in the periodic table. Virtually every element on the periodic table, essentially everything heavier than lithium, is made in stars, and a lot of helium and lithium are also made in stars. And so if you want to understand this, you have to be able to look at how the abundances in the galaxy unfold over time. When we look at the oldest stars, we see that many of them have very few heavy elements. A pattern develops over time. It is different in different parts of the galaxy, and this tells us a great deal about how well this periodic table came to be. Another thing is an example is trying to figure out how our galaxy formed at all. This is a brief little zoom-in simulation by Phil Hopkins' group at Caltech, kind of showing you an example. This is not a galaxy, this is a galaxy in a box, a simulated galaxy, where you take a whole bunch of different ingredients and you try to put them together, starting with smaller blobs, building larger ones. And by doing this, what you can do is you can then try and see if you can understand how galaxies in general formed, how our galaxy formed, and the role of important things like ordinary matter like us, dark matter, which has gravity but doesn't interact, dark energy, and other features. Now, the reason why I like looking at this, well, to be truthful, I get to be a shameless person who piggybacks on things intended for other purposes, okay? So nobody would build a giant fancy space telescope to do just what I do. But it turns out that if you take movies of the sky, stars rattle around, stars vary, and you can learn really great things by studying how these stars vary. Now, if you wanted to be able to figure out how the galaxy formed, if you wanted to be able to figure out where elements on the periodic table came from, you'd want to look across the galaxy. And that's why red giants are fantastic. Red giant stars are bright, they're like searchlights. You can see them halfway across the galaxy without effort. In fact, you heard earlier about the Roman Space Telescope. One of our big problems with Roman is that the red giants at the center of the galaxy are saturated in the Roman images. They're saturated in the first 1.5 second read. So that's, first of all, how fantastic Roman is, and second of all, it gives you a sense of how bright these giant stars are. And in addition, it turns out to be really easy to measure the abundances of the heavy elements in giants. And so that means we have these great searchlights that you can look at a long ways away, which are amazing diagnostics of what things are made of. And you would think everything would be really easy. On the right-hand side, here's an example of the outcome of what we do, measuring ages across the galaxy. But you have a basic problem here. Your basic problem is that the things you know about locally are actually quite different potentially than the things far away. So you can't just look at the galaxy up close to be able to figure out what's going on. This is a great example from an important paper about 10 years ago from the Sloan Survey, something Ohio State is part of. The Sloan Survey is a gigantic telescope which takes thousands of high-resolution spectra of stars, in fact, more than 1 million at this point, and analyzes them in an automated fashion to get abundances. The 3 panels are looking at the galaxy from the midplane up a little bit, up a lot. Each circle is a different radial ring of the galaxy. We are the red circle, that's where we live, down at the bottom, okay? And you may notice that there's this y-axis is something called alpha to Fe. This is a measure of how important collapsing of massive stars is. Stars that are massive collapse and make a lot of what we call alpha capture elements, oxygen, magnesium, things like that. And on the x-axis is iron, which comes from 2 different sources. It comes from exploding white dwarfs and from explosions of massive stars. These things take different amounts of time. And what I want you to draw on from this picture is you notice that where we are, everything is kind of clustered around solar abundance. That's 0 on this scale. And there's this little frosting of stuff that's a little bit higher. But if you go to the center of the galaxy or up, the pattern gets completely different. Okay, so the mix of elements that you see in the galaxy completely changes as you go from place to place. There's more things that got made fast. That's the way to interpret the stuff at the top. The abundances change, but this diagram tells you absolutely nothing about how long this took. All you know is what the stars are made of. You don't know how old they are, and that's why we want to be able to figure out their ages. Basic problem with giants, unfortunately, is they're kind of all the same to first order. You look at them and they're all red, they're all very similar in color, they're all very similar in properties, and so as a consequence, that means that it's incredibly hard to figure out ages for giants. So historically, we knew that we had these fantastically bright stars you could see a long ways away that could tell us something, but we didn't have any tools to figure out how old they were. It was just too difficult to do. And the figure on the right is just showing that if I change my ages by a huge factor, 2 to 12 billion years, it looks a little bit less than changing their abundances by a factor of 2. It's incredibly hard to measure their properties. And this ties to something else, which is that really, to some fundamental level, we only get to see stars at the surface, right? So you see a star at the surface, and the star doesn't necessarily tell you the things you'd like to know the most. It doesn't tell you its mass. It doesn't tell you its age. They're kind of like people that way, perhaps, a little bit. You know, they don't want to share that information so readily. And even how far away they are is actually kind of hard to figure out. But the key thing is, it turns out that this business I talked about earlier, taking movies of things, actually makes an enormous difference. Because if you can take movies of things, then all of a sudden the way stars change, the way they vary, has a lot of information. The outer layers of stars are turbulent. That's the first thing. This is a snapshot from the Swedish Solar Telescope, a gorgeous telescope. This is kind of a time-lapse movie showing that picture we're showing is bubbling and boiling. The surface of the sun is a giant boiling kettle where material is being carried from deep inside the interior. It's almost a 200,000 kilometer thick layer of boiling plasma in the outer layers of the sun. So there's sound waves, but in space, nobody can hear you scream. So given that, how could you possibly be able to hear this? How could you know that you do this? Because I said, well, there's turbulence. You make sound waves, just like a cello is different from a violin. You should be able to do something with those sound waves to figure out what the thing is made of. But what you do is you take advantage of the fact that when you have waves moving around in stars, pieces of the star are moving in and out. You're creating standing waves in the star when you have this turbulence. One of these is a pressure mode, what you're hearing me from, and that's our main piece of information in stars is pressure waves, where basically the air is going back and forth between you and me in the line of sight. Another is a water wave, just like waves on the ocean, where cork is bobbing up and down and the wave is moving perpendicular. And so enormously centrally concentrated, and the waves bend. If you put a stick in a tub of water, the stick looks like it bends, okay? And by the same token, what's happening here is the surface of the sun has a density 1,000 times lower than the air we're breathing. Okay, it's almost a vacuum. The center of the sun has a density of 160 grams per cc. It's basically 160 times denser than water, denser than lead, denser than the densest rock. And so if you start with a vacuum and you have a dense thing in the middle, you send a wave in, and this kind of pattern shows you what you get. You're going to get waves that refract. And if they come back to the same place where they started, you get constructive interference. And if you get constructive interference, you have a standing wave. And a standing wave means some places are going to be going up and getting cold, other places are going to be dropping and falling. So now I'm going to have patches on the surface that are bright and dark. Okay, this is the basic piece we're doing here. And in the sun, we can see fantastically complicated patterns because we can resolve the surface. But even if you don't resolve the surface, you can get some other things. I've shown you here a couple of images of what the surface of the star does in a couple of these modes. There's a whole bunch of these that are fun. There's also the one that's water sloshing in a pan where one side of the star gets bright and another side of the star gets dark, things like that. So we have a huge number of these modes. And we know that what they're telling us is they're telling it how long sound takes to get from one part of a star to another, okay? Because you're measuring the speed of sound. The speed of these waves is the speed of sound in stars. And so the basic summary here is you have boiling kettles on the outside, you have waves that get refracted. This causes variation in brightness. And you may notice that if you see these 4 stars, the smallest star down near the bottom has a low amplitude of variation. Then as the stars get bigger, you notice the amplitude of variation gets bigger, but you also see it looks like they're changing more slowly. They're changing more slowly because the bigger things aren't as dense as the smaller things. The frequencies are actually lower. And so if you run this through a Fourier transform, we call it, you figure out the frequencies of variation, you see that you get these sharp spikes, which are the individual modes. You actually get to observe each individual standing wave with a different frequency. There's a bunch of pieces of these frequencies. I'll skip over the details, but you can just visually notice that down here, if I'm looking at an object, which is, as I basically have an object which is like the sun, the frequencies are high and they're spread apart. As you go down, the frequencies drop and basically they get closer together. And so we analyze these with automated tools, and I've just told you now how you go from a bunch of turbulence to taking a movie of a star to getting these frequencies. One of these things tells you about basically the density, the other tells you about the gravity, and I can get mass and radius this way. So this is how we get masses and sizes and ages of stars by just taking movies of them. The fantastic thing about this is it doesn't matter whether it's close or far away. These frequencies don't care. If you can measure them, you've got them. And I'll skip over these pieces here. And now the next piece I want to get to before I get to Roman is it's important to understand why we would even bother doing this with Roman at all, okay? Because we started with some telescopes, and you might think, well, you did it once, you figured it out, you're done. You know, so why would you need different missions? This is showing a couple of the close missions. What you're looking at here is a cumulative distribution. This is how many stars we've been able to do this seismology for, as a function of how far away they are from us, okay? And so the Kepler mission was an enormous mission. It was a great thing. You probably heard about it in terms of planets. The Kepler satellite studied 156,000 stars. They found thousands of planets around other stars by looking for the shadow of the planet on the surface of the star as it eclipsed the star. They also took movies of all those stars, and we got tens of thousands of measurements of these oscillations in these stars. So we basically shamelessly hijacked a planet mission, and we took all of their movies and did something completely different with them that they had not envisioned at all. That's the great thing about science. You can do things that you didn't plan on doing in the first place. Now, all of these missions were great, but they tended to find things close to us. The center of the galaxy is about 8,000, 8 kiloparsecs away, 8,000 parsecs. So all of these measurements are for things that are pretty close, okay? Now, the TESS satellite, have you heard about the TESS mission here? The TESS satellite is a fantastic tool, but the TESS is a great example. It's a camera that literally takes an image here to there. Okay, so it takes a slice of the sky like that for 27 days, marches around, goes around a hemisphere once a year, flips, does another hemisphere, all sky. But you want to know what its resolution is? It's your eye. Things you can make out with your eye are about the same as things that TESS can make out. It has 21 arcsecond pixels. Okay, so that means that TESS is fantastic, but big pixels, stuff that's close. So TESS finds a ton of things really close to us. Helpful, but not exactly what we're looking for. So Kepler gives us this fantastic image, and Kepler in many ways was a weird way to start this science because they took the Kepler satellite, they parked it on Cygnus for 4 years, they stared at this patch of sky, took a movie every 30 minutes, we got fantastic data. And it turned out that since this was not designed for this purpose, this was designed for planets, this was roughly the equivalent for our science of throwing basically dynamite in a barrel and hunting for fish. So we got basically signal to noise of infinity spectrum. We got just this fantastic data. And that means that we started this business with the most fantastic data you could probably ever hope to get, right? So that's great. But the issue was that you basically could only get this for a pretty small number of objects. And the other thing is Kepler is perpendicular to the center of the galaxy for us. So Kepler is basically telling us about sort of the neighborhood we live in. It's telling us about the solar circle. When you do this, you get beautiful stuff. The color coding on this diagram represents measures of the heavy element content of stars, for which we have exact masses on the left, and measurement of stars with exactly the same composition but different masses on the right. And the point is that stellar theory tells you that I should go from basically low metals to high metals. Things should move from left to right. And the data does. It's just gorgeous. This is data, not theory. And the data is indistinguishable from where you would basically put your theoretical dots. It's just fantastic. You can see that stars of different masses show up. This is showing you the radii of stars that we believe are burning helium in their cores. Stellar theory predicts there's a sharp lower edge in the size of these stars, and there is a perfectly sharp lower edge of these objects. Right? There are thousands of points on these plots, and it's not very often I can put thousands of points on a graph and have like one or two of them stick out. That's a sign the data is fantastic. Okay. You can also use this to test populations. I want to show you this because this diagram actually has a lot of really beautiful features here of stellar populations that are kind of worth talking about a bit. I've broken stars up. Remember I told you there were stars that had a low, what I called alpha abundance? That's the things on the left. There's stars with a high alpha abundance. That's the thing on the right. The size of the star is plotted here. The mass of the star is plotted here. Look at the red points first. The red points are stars where we can look at the patterns and tell that they have to be what we call normal red giants. They have to have a little white dwarf in the center. Their frequency patterns tell us the properties of the core. The blue points are a completely different kind of star. These are these core helium-burning stars that I talked about. They have a fluffy core. Their frequency patterns look different. So we can look inside the star and tell whether the density is 1,000 times the density of water or 1,000,000 times the density of water. And so these blue and red points are distinguished just by the cores, nothing else. So if you look at the giants, you see this lovely little sharp edge here right around 1 solar mass. You notice that there's almost no red points on the left-hand side of that. That's the age of the disk of the galaxy. Higher mass stars actually have a shorter lifetime. Lower mass stars have a longer lifetime. Stars below about a solar mass haven't had enough time to get to this stage yet. This is a proof that the disk of our galaxy is about 8 billion years old. Okay. If you looked at these red points carefully, you notice they're a little bit on the left of the one instead of a little bit on the right of the one. That's because this thick disk is about 9 billion years old. So you can use this to pick out clues like this to figure out how old the galaxy is locally. And of course, there's a whole wide range of masses here, which means there's a wide range of ages. We can use this to construct a chronology for the galaxy. Now at this point, this is where my AI friends say, oh, we don't need you anymore. You've decoded this pattern. We're just going to look at a whole bunch of stars. We're going to say, what are there things on the surface? Let's let the robots do the work, and the robots will just tell us everything about the inside. You've given us your test suite. You've given us your cases. We're done. Go away. Fortunately for us, that doesn't work, or at least it doesn't work in sufficient detail because I told you the stars were different in different parts of the galaxy, right? Well, if it turns out there's certain stars that don't live here, and if you don't have a star that lives here of a certain age and composition, you can't train on it. And so as a consequence, it turns out that these tools only work in cases that are kind of like the training set. So if we want to know about the center of the galaxy, we have to look in the center of the galaxy. Good news for us. Job security, if you will. I will be John Henry, hanging my little hammer until the very end, put it that way. K2 was a beautiful alternative. K2 was this great MacGyver follow-up to Kepler. where basically Kepler's gyroscopes broke, but they figured out that the solar wind was kind of like a gyroscope. And so if you basically use the solar wind as one of your gyroscopes and you just shoot your fuel very, very carefully, you can kind of sort of point at one place, and they got fantastic data. But it was only looking for a short time, so it went around the galaxy. As I mentioned, TESS is a huge but a local sample. And this is where Roman comes into the picture. Now, the first thing to know is that Roman is a fantastic telescope. It's one that is currently scheduled for launch in October 2026. And it actually has several distinct missions that it's going to do. Some of Roman science is what I'm going to call survey science, like it's put up to do a certain thing, okay? And other of its science is just open for people to basically put in proposals for. The things it is intending to do are to try and understand dark energy and the fate of the universe, to try and understand the distribution of planets around stars, and also to try and basically do things like take big maps of the galaxy, okay? And so as a result, Roman is actually a multi-purpose telescope, and it really has some individual investigator capabilities. Kepler, by contrast, the mission I told you about, was designed to do one thing. It was designed to look for planets, and anything else you did had to sort of be complementary with the main science. You couldn't actually just tell it to do some completely different set of things. And so the very first thing they said they were going to do is, well, we want to be able to study micro-lensing of planets in the galactic center. So we're going to take movies of the center of the galaxy every 12 minutes for 400 days. And I was like, yes, yes, yes. Because as soon as you're going to do that, I'm in business, basically. You're looking at one patch of sky for a year, every 12 minutes, I'm golden. And then it's going to do fantastic things that I don't do and other people can talk about, like looking, for example, at exquisite measurements of the shapes of galaxies to do what we call weak gravitational lensing, and use this to test the expansion history of the universe. And there's also going to be fun things like working on a coronagraph. Now, the Roman telescope itself is almost completely assembled. And this movie here is a description of the camera that I thought might be interesting to this audience. So I'm going to play it for about a minute. And we'll see if it actually has sound.
Is the heart of the Nancy Grace Rowland Space Telescope. It is one of the breaking space telescope to take pictures with the same detail as Hubble, covering an area 100 times larger. Despite this incredible power, the basic design is the same as telescopes around the world. Light enters through Roman's 2.4 meter aperture and is reflected and focused by the curved main mirror, which is also the largest green telescope. This light is reflected and focused once more by the second four elements lightning constricted to stray light rays before it passes to the filter mill. With filters that allow different
Accessibility shortcuts. 17 items.
Sorry.
We just made contact.
Don't try to do things when you don't know how to do them.
Oh, we just made contact.
Sure.
and probably the one time did this the best. He says, I stayed these questions. Says there are 18 detectors, allowing it to create 300 million pixel images of large patches of the sky. The large number of detectors and pixels gives Roman wide field of vision. The size of the mirror and the precision of its optics is Roman's wide image. This combination of image size and detail has never been possible on a space-based telescope before, and will make the Nancy Grace Rowland Space Telescope an indispensable practice in the future.
Yeah, this set of properties really is completely unprecedented. And we can give NASA thanks for the video there. One note is because this data sets are so fantastically large. Remember, 300 megapixel camera taking snapshots every 12 minutes for a year for the galactic bulge, okay? Hundreds of millions of individual targets. They're actually not going to be giving us data to download. They're going to do it all in the cloud. And so Roman's going to have a platform. Anybody in the world can go up. NASA will basically produce light curves every 3 days. And basically, if you want to do it, you just log in, and they basically give you these supercomputers for you to do your stuff on the fly. So it's actually going to be a really interesting, normally we download data on our own computers and do stuff. And so this is actually a very different model, and it's necessary because of the enormous data volumes we're talking about here. And so this is the idea. We're going to be looking at the center of the galaxy. And the basic science behind this is gravitational microlensing. This is a beautiful, beautiful technique. And the main impetus for doing gravitational microlensing studies in the galactic bulge is that all of our planet search methods that we currently use are very biased, okay? We basically can measure the shadow of a planet passing in front of a star, but that favors things that are relatively close. It favors, it makes it very hard to figure out what their mass is. We can study radial velocities, the gravitational pull of a planet on a star, but the problem is little planets don't do much. The Earth doesn't pull on stars very much, and so it's very, very hard to find Earth-like planets in Earth-like orbits. By contrast, gravitational microlensing relies upon the fact that mass bends light, and so as a consequence what we're doing is we're waiting for a star to move in front of another star. The star that moves in front bends the light of the thing behind it, which is the bright thing, and as a result it tends to amplify it. You can kind of see what's happening with these things. They line up perfectly. I have a closer star lining up with a further star. It brightens the star. And the idea is, what happens if the star in front is dragging a planet with it? Well, the planet gets in front of the star too, and the planet creates a little dimple, which actually you can see. This is a way we can find planets like the Earth, and so it's fantastic for that purpose, okay? The issue is, remember I told you the thing in back is bright, and the thing in front is faint? This means you're not seeing the star that the planet's orbiting around, and you're also not seeing the planets themselves. So one of the jokes my colleagues have is microlensing is a great way to find planets that you can't see, orbiting around stars that you also can't see. So it relies upon a certain degree of data analysis to make this stuff work, but that's what my colleagues like Scott Gowdy are superb at doing. And so this is the difference between these is that this is in principle going to be able to measure thousands of planets, including planets and systems that are like ours. And so the goal of the planet science of Roman is to be able to figure out whether our solar system is normal or not, because solar systems like ours can actually be found with this telescope much more easily than with our other tools. For those of you interested in the details, this is sort of roughly a 0.9 to 2 micron filter. This is infrared detectors, and so for those of you interested in how detectors work, this is actually really different. An optical detector basically saturates when you look long enough. What happens in infrared detectors is the voltage difference drops to 0, and so as a consequence, an infrared detector just loses sensitivity when it saturates. It doesn't actually bleed pixels and things like that. It takes it, and rather than this being the kind of thing to where you stop and take an exposure, you're reading the chip every basically 50 seconds. So you're continuously reading the chip from top to bottom every 50 seconds. And when we say it's a 15-minute cycle, what we really mean is we read the chip, move the telescope, read the chip, move the telescope, read the chip, move the telescope, and then just roll back so basically you do 7 fields every 15 minutes or 12 minutes, depending upon the details. Right? So it's continuously reading out, continuously collecting data, moving every minute, and in our case, our stars saturate in 1.5 seconds. So fortunately, we get them to do sub-reads, so we get to read the first 1.5 seconds and the full 1 minute or 50-second integration. This is an example of a single piece of the field. This is 1/1000th of the image that we're simulating in the galactic bulge. Our job is to produce a light curve for every single object in this. Or the planet people's job is to produce a light curve for every single object in this. I have a happier job. You see those annoying little yellow things there? Those are mine. Those are the giants, okay? Those are the bright objects that we're going to be looking at with this telescope. If you zoom in, you can now zoom in and see what it looks like if you're looking at a much smaller piece of it. And then if you go to the various filters, you get down to a few arc seconds. The point is, this is Hubble Space Telescope resolution. So this is a window, which is basically October 2026 to May 2027 for launch window, coming up against potential chaos monkey complications I'll get to at the end. There's no reason why the launch has to be delayed. It's on schedule and on time. It's extremely high resolution. And the other nice thing about this project is it turns out that the very first thing they're going to do is look at the galactic bulge. So basically they're going to launch it, and 3 of the campaigns, basically 3 of the first 6 months of the thing are going to be taken looking at the galactic bulge, which means this science is the starting science. They're then going to come back to it in 5 years and finish it at the end of the 5-year mission. And the reason to do that is it turns out you can look at the motions of stars during those 5 years and in effect use those to back out the distances exactly to things in the middle of the galaxy. So we think we're going to be able to get distances to stars in the center of the galaxy to about 1%, or better based on this, which is comparable to what you can do here locally. Okay. Now our initial work, we're going back a few years, we had some papers that said, let's take a light curve that looks like Kepler, let's see what we think the signals are going to look like, and yeah, we think we can probably do it. And so we simulated with computer with rough estimates of what things were. What we've been doing over the last 2 years is to do a much more detailed job of this to make the case to the mission that this can be done. The other reason why we had to do this is one of the great things about NASA is if you tell them that you needed to do something different, this is the stage of the mission where they might listen to you, right? So if you tell them that you really need to look more often or do a more precise job or whatever it is, you actually have the possibility of doing that. So our basic idea is we think that we can get more than 400,000 stars in the center of the galaxy with this technique. And of course, this goes with the many thousands of planets. We'll get ages for them. We'll get abundances for them. And what that means is we'll also be able to do something very useful for the microlensing people, which is they'd kind of like to know what the age of the population they're studying is, and we can measure it with the giants. So we can actually tell them something about the ages and things at the center of the galaxy. And to be clear, this is a surprising, poorly studied piece of the galaxy, and we could very well find that there are really, really strange things going on in the middle that we didn't know about. That's why you do science. So we did various simulations, looked at different noise models, and one of our key things here is, remember I told you that this mission is going and going back. Well, it turns out, remember I told you Kepler just stared? Well, one of these things has less noise than the other thing does, and it turns out moving it a whole bunch of times can give you a lot of noise, and so the noise floor is actually a significant problem. Internet if you care to read these things. And our bottom line is we convinced the mission to actually adjust their timing. Our initial simulations here said 15. They're now actually going for a 12-minute duty cycle instead. We actually made the case that was a little bit better. And the other thing that we've done that's fun is the original microlensing campaign, go back here, wasn't actually looking at the center of the galaxy. The center of the galaxy is at 0, 0. You notice there's nothing there. That's because it's really heavily obscured, even in the infrared, and it's tough to do. But we said, you know, you gotta look. I mean, you're taking movies for a year. You gotta take movies in the center of the galaxy because you never know. And they bought that, believe it or not, and so they're actually going to be looking in the center of the galaxy as a consequence as well. So the bottom line here is that we think we're actually going to be able to get a huge number of these things. And we're also now moving to the next stage where we're trying to do things like see if we can figure out how to do things like saturated star photometry. In that regard, NASA is again wonderful. They actually did some experiments for us where they actually exposed the detector, saturated some little images. So we actually have real data for how saturated images behave, and we're kind of processing that data to see if we can figure out how to use some very clever little tricks to extract information from this. Basically, if you've done astrophotography, you know diffraction spikes. They may be your enemy, they are our friend because the diffraction spikes don't saturate, and so as a consequence we can actually get information from the spikes and the wings of the images, which is what we're doing. So given all of that, see if I can. Oh, I'm going the wrong way instead of the right way. It's like, this is just going on for a while. I don't know. And so the bottom line here is that we're now actually have a beautiful series of missions to work with. We have the original legacy work from Kepler that gave us fantastic high-resolution data about stars, about 16,000 stars. We are currently working on data from the TESS satellite. We think we're going to be able to get somewhere between 160,000 and 320,000 stars, very locally in the galaxy. We'll be able to use this to make a detailed map of the history of formation of our local galaxy, which will be great. And then in Roman, we think we're ultimately going to get more than 400,000 objects in a completely different place in the very middle of the galaxy. Now, one last thing I will note here before I close is, you know, it'd be really great if you could contact your congressmen and senators because the executive branch just put out a budget that basically cancels all of space science for NASA. Not just some of it, all of it. Well, no, they'll let the Hubble Space Telescope fly because people like it. And they'll let JWST fly because it's relatively new, but they're literally talking about shutting everything else down. Now, fortunately, we do not yet live in a monarchy, and so it's possible that this can be changed. But it'd be really, really great to have that not happen. In fairness, even Ted Cruz doesn't want that to happen, so I don't think it will, but it'd be really good to do that. I really appreciate y'all's attention. I hope this has been good, and I'll open up for questions. Thank you.
Flooded by the data. It sounds like it would be overwhelming.
Oh yeah, that's one of the really sobering things is that we were, because my colleagues, when they were doing these original things, it's like you do one star, you click a button, you look at it, it's like, great, you know, it's like there's 400,000 of them.
Okay.
You can't do that, right? And so
That's why you have a centralized computer.
Yeah, we need the computer to do that, but even if you do that, one of the challenges you always face is we show you the lovely stuff, but what we don't show you is that the 10 or 20% of the time the data is ugly and it has to be worked with, right? And so 80% of the time it just works, it's beautiful, and then 20% it doesn't. The problem is 20% of 400,000 is a lot of troubleshooting, right? And so a lot of it depends. I think in this way, there's a lot of properties of this that are fantastic because the data is very high resolution. That helps. You don't have blending, right? So there's advantages. But yeah, it's a big data problem. Yes.
So you said it's doing video.
Yeah.
Yeah. Is a 12-minute time lapse with a photo every 12 minutes, or is it an actual video recording?
What they're doing is they're recording an image for 50
That's on one piece of sky. Then they're timing to 7 different places in the sky, and they're coming back to the same place every 12 minutes.
Oh.
Right. So it's a video on different scales. Actually, you get information on less than a minute. You get the information on the exposure band. You get the information on the 12-minute cycle as well.
So what are the frequencies you showed the Fourier transform of the star brightness variations, which gave you the various frequencies that the surface of the star is, I guess, you just vibrating in.
Yeah.
So what are the frequencies we're dealing with? Is 12 minutes good enough to capture
Yeah.
everything that we're dealing with?
In the sun, it's 5 minutes, so you can't observe oscillations in stars like the sun.
Okay.
But when you get to these red giants, the ones more interesting, the periods of like 12 hours, they're very low density, 12 hours to days to weeks to months.
Okay, so there's so low density that the pulsations are much less frequent.
And that's actually why the Kepler mission worked for us perfectly. They wanted to find an Earth-like planet around a sun-like star.
Yeah.
That takes 2 hours. They need 4 30-minute exposures. And if I was designing what I would want for giants, 30 minutes. Perfect.
Didn't we take the Kepler data, like the entire Kepler data, that one field, and just make one really freaking deep image of the, I don't know, intergalactic flux in the galaxy or something like that in that region?
Yeah. They've done some of that. It's a white light mission, and so Kepler was a little bit different design.
Yeah, but that makes.
Yeah.
So I do variable star astronomy. With variables, you're looking at the overall brightness as it's pulsing. How do you break it down so that you're actually looking inside of the pulse?
Well, the idea is we're looking at modes that are low enough order that the brightness of the star is actually changing. So, for example, the lowest order pulsation mode is what I call the water sloshing. You carry water in, it sloshes back and forth.
Right.
So one side of the star gets bright, one side of the star gets dim. Right? And so as a result, if you have a wave like that that's going, the whole star is going to get slightly dimmer or slightly bright. The amplitude of this is about a millimagnitude, one thousandth of a magnitude. So it's not high. If you look at the bright giants, it might get up to 1% or a few percent.
Okay, so you're looking at the individual. It's like if you're looking at the pulse, you're looking at the individual, the movements inside of the overall brightness and stuff.
Yeah, but the complication is we're looking at all the modes at the same time.
Okay.
Right. And the other problem here is this is turbulence that's making these things. There are two things that are hitting each other, so some wave rattles around.
Right.
But that's not going to be steady. It's not going to be like a pulsing, a Cepheid or something like that. Because what's going to happen is there's going to be a whole bunch of these little signals going off at once. So they'll keep a frequency, but they won't keep a phase.
Okay.
If that is. Thank you.
So doing it over a long period of time, you get more signal basically and less noise because you have several cycles that you're sampling.
Yeah, and you just have to wait for things to be favorable. It has 3 waves crest at the same time, so the planet gets a little bit fired or something like that. So if you wait long enough, the thing snaps into focus. But if you look at it for a short time, you just see
Very
noisy stuff that you can't resolve. So it's a different kind of variable star study.
So how safe to building some of the actual equipment for this? I know in the past they built some of it.
We're involved in a lot of the data analysis teams, but no, don't do that. JPL, all the way.
Okay.
Northrop Grumman, big name people like that, big bucks for that stuff. And in addition, some of the telescope was donated from a reliable, the mirror was donated from a reliable, highly used program.
And tested properly.
Tested properly. They're very great. Yes.
The idea about chemical evolution mainly, someone had done this, they observed oxygen in the atmosphere, crushed all magnetic base.
Yeah. That's the kind of thing we're looking for. We're finding, for example, with the James Webb Telescope, that we're seeing stars and galaxies forming somewhat surprisingly early in their history. And we're getting some indication of the origin of the elements occurring rapidly in these stars. And so that's one of our motivations, in fact, is to see if we can reconstruct our history here and see if the history here in the oldest stars sheds light on what's happening in the distant galaxy. So, but yeah, that's exactly what we're trying to do. We're trying to see what, if you look at really old stars, is the oxygen strange compared to the oxygen that.
Is Roman going to take pretty pictures so that the public can say, we got another cool space telescope out there?
But this will take fantastic pictures. It will take. I mean, this is really like 100 times helpful. So I'm not exaggerating when I say that we want to do Andromeda. In fact, one of the proposals me and my colleagues are looking at is literally to do that. To say, you know, it'd be a great idea. Let's stare at the Andromeda galaxy for a month. Something interesting will happen. Or stare at a globular cluster.
If that will capture the public's attention,
Right. You mentioned that teams out affiliated with Ohio State. Is there other projects on that's going to use this data, such as in my areas, chase filter, star spots?
Yeah. Well, there are other teams that are working on rotation, eclipsing binaries, classical variables. There are teams working on planet microlensing, looking for supernova explosions, looking for exploding stars, and also on studying this weak lensing work. So that every one of those groups has some representation here. The rotation period stuff is being led by a group at Goddard in Florida. There is a group working on that. Yes.
I wanted you to tell a little bit about the difference between Roland and what is that Sphere-X, which was a telescope launch last month.
Yes. They're very different kinds of purposes. Sphere-X is a fantastic telescope. It's taking basically spectrophotometry. It's actually being able to take a detailed spectrum. And so as a result, Sphere-X is actually covering a much wider range of wavelengths. Roland is basically a red, 0.9 microns in red to infrared image. Roman is trading it off against with an incredibly large field of view and a large mirror, incredible sensitivity. So Sphere-X is going to tell us some really interesting things. So I'm looking forward to using the Sphere-X data for a lot of purposes. But it's just going to do something different than Roman's.
Cynical.
How about the Garrett Rubin telescope in the south?
Yes, that's also going to be coming online, and that's another interesting, there's a very interesting set of suite of capabilities. In this case, the idea is that they're going to have a absurdly large camera, one that makes Roman look tiny. And the goal is to snap a pretty high resolution image of the entire sky, accessible to the telescope, at least half of the sky that they can do, every 3 to 4 days. This will help find asteroids and things like that. For the kind of work I do, 3 days is kind of a leisurely pace to be sampling the kinds of things that I'm doing. So even for rotation, that's actually kind of slow. So it's really interesting for a lot of purposes. It'll be fantastic for supernovae. It'll be fantastic for transients and other things. Very long period varieties. But it's actually designed, again, for a different purpose.
Yeah, it's two-star.
Yeah, I was going to say, imagine all the new variable stars that they're going to find with this data, because they are long period, like Cepheids and stuff like that. But the amount of the new variable stars that might be coming out and what that might be able to tell us.
The Rubin telescope M-dwarf flare rate is 1 hertz.
Wow. Yeah.
So there's going to be plenty of data of flaring M-dwarfs.
Sure. Rubin, that's 1 a second.
Yeah, 30 million a year. Yeah, give or take. They're actually having data handling problems, so it's a real issue. Like what they actually download, it becomes more like virtual physics, where you decide to download a subset of data.
You use with petabytes or something.
Yeah. And Gaia is releasing its data release 4. It's time resolved data, and they're saying that's going to be a 500 terabyte data set.
Here. Isn't that there? I think we don't know.
Yeah. So we do live in the future.
Yeah. And in the past.
And very much in the past.
Any of the funding coming from, say, ESA or other, just all the U.S.?
This is all NASA. There are different missions. Europeans have some very interesting missions that they're doing. The Plato mission is going to be launched about the same time. But that's purely funded by ESA. It's not funded by, it's not funded by us. And the Europeans are ahead on building a large ground-based telescope, extremely large telescope. So they're building the next generation big ground-based telescope, and it's very likely that would be completed well before the U.S.
Where is that going to be?
That's in Chile.
So that's,
And Japan and China are also launching satellites. India, the Indian Space Agency. So there's a lot of other things that are kind of cooking in the pipeline. This is a very interesting news.
well, it's huge radio telescope at Southampton.
Yeah. GOES. SKA, yes. Square kilometer array.
Okay.
There.
Well, thank you so much.
Thank you.
Great story.
Appreciate it.
Yeah.
So next month, Jason is going to be talking on his adventures with C-STAR and the various things he's done with it. So we learned about the telescopes last year, and now we're going to see some of the results of what he's been doing. So,
There's some photometry and astrometry.
yeah.
Thank you so much. Appreciate it. What else?
Well, he's done it.
Okay. You take care.
So, before we close out, any questions anybody had about anything else? Yes. And once again, I'll remind you, anybody that's new with scopes who has questions, they can ask us or bring their scope, and we can try to help them sort out odds and ends, after meetings and stuff. And hopefully we won't be wandering around to different places too much longer, but we'll have to see. So we'll keep you informed. Don't forget to check your email. And I guess that's about it for the moment.
Check your spam folder too.
Yeah, that's right. If you're having trouble receiving time focus or anything, make sure you've got the what is it? IO address. Yeah, in your contact list, because if it's not in contact list, the servers might help in the spam folder. That makes so. Okay, thank you for coming out in spite of the rotating out location.